Deep in the vast expanse of our universe, it's not just stars, galaxies, and the black void of space. There's also a mysterious force at play, driving the very expansion of the cosmos. This is a story of dark energy, dark matter, and normal matter. These elements, in their varying proportions, craft the intricate tapestry of our universe. The radiation from the early stages of the universe, a remnant from the Big Bang, plays a role too, but not as significant as you might think. And this cosmic expansion, it's like raisins moving apart in a leavening ball of dough, the space between everything stretching. Yet in this vast dance of cosmic forces, dark energy remains a constant, a never-ending wellspring, making more space as the universe expands. And as for the energy distribution across the universe, well, it's a story as old as time, with its clues hidden in the redshift distance relation across cosmic history. But hold on to your hats, listeners, because the most captivating part of this cosmic tale is... oh, you'll hear about it soon enough. Hey there, curiosity explorers. Are you ready for another dive into the unknown? I'm your host, Cesar, and joining me is our brilliant commentator, Sonia.
Hello, fellow knowledge seekers. It's always a joy to join you on these exciting journeys of discovery.
And we're thrilled to have you along for the ride, Sonia Guimarães. And to our listeners, we'd love to hear your thoughts and questions. So don't forget to subscribe to our show, Curiosity Wonderland. Leave your comments and share our episodes with your fellow curiosity explorers. Let's dive deep into the mysteries of the universe together. Let's go deeper into the cosmic mystery. Picture this, our universe as a giant ball of dough filled with raisins. As the dough rises, the raisins move apart. This is similar to what happens with galaxies in our universe. As the universe expands, the galaxies within it seem to move away from each other. Why? Because the fabric of space itself is stretching.
And that's why we say the universe is not just expanding, but it's accelerating, right?
Exactly. This acceleration is driven primarily by dark energy, which accounts for a whopping 68% of the universe's energy density. Following that, we have dark matter making up 27%, and normal matter, protons, neutrons, and electrons, accounting for about 4.9%.
So, if I understood correctly, things like neutrinos and photons only make up 0.1% of the universe.
That's right, and they behave as forms of radiation. A significant portion of this radiation is left over from the Big Bang, the result of massive particle-antiparticle pairs annihilating each other. Now you may wonder, if so many particle-antiparticle pairs annihilated each other, why doesn't radiation play a bigger role in the universe? Well, that's a great question.
Wait, don't tell me. We're going to explore that in our cosmic journey, aren't we?
You got it. But remember, the universe is not just full of surprises, it's also full of secrets, patiently waiting to be unlocked. To visualize this expansion more clearly, think about the raisins in our dough. Now, as the dough rises, the raisins don't actually expand themselves. Instead, they stay right where they were initially placed, while the dough around them expands.
So, the dough represents the space, and the raisins are the stars and galaxies, right?
Exactly. Now, over time, as everything continues to expand, the universe becomes less densely populated, a bit more sparse and more diluted. And the light that travels through this expanding space also experiences changes.
Changes? How so?
Well, when light is emitted from a source, it carries a specific wavelength. The longer it has to travel through the expanding universe before being absorbed by an observer, the more its wavelength gets stretched or redshifted.
So the expansion is literally stretching the light?
Yes, this stretching is directly tied to the energy of the radiation. The energy of light is defined by its wavelength and two constants, the speed of light and Planck's constant. As the universe expands, so does the wavelength of light. If the expansion doubles the size of the universe, the wavelength is also doubled, causing the energy of the radiation to be halved.
So the energy is inversely proportional to the wavelength. But does this change affect the galaxies themselves?
Great question. While the properties of the radiation, like its wavelength and energy, change as the universe expands, the matter, the galaxies or our raisins, don't actually change themselves. but they do become less dense as the volume of the universe increases.
And this dark energy you mentioned earlier, what role does it play in all of this?
Dark energy, along with the field energy during inflation, is a form of energy inherent to space itself. As the universe expands, these forms of energy play an increasingly important role. But that's a topic for another deep dive into the cosmos. Now, there's a third form of energy in our universe that is neither matter nor radiation. This, my dear listeners, is dark energy. As the universe expands, the matter particles don't change, but their overall density decreases, given that the same amount of particles occupies larger volumes.
Like spreading the same amount of raisins in a bigger dough ball?
Exactly. As for quanta of radiation, their individual energy drops and their wavelength stretches as the universe expands. They too drop in number density just like matter, causing the energy in radiation to decrease faster than matter's energy density with continued expansion. But dark energy doesn't play by these rules.
How does dark energy behave then?
Dark energy behaves as space itself. It creates more and more of itself within the expanding universe. Its energy density does not drop as the universe expands, but remains constant. This is why at later times, dark energy comes to dominate the energy budget of the universe.
So earlier in the universe's history, matter was the dominant form of energy, but now it's dark energy.
Absolutely. Consider it like this. In a concert, the musicians, matter and radiation, start playing louder and louder, filling the auditorium with sound. But over time, as the concert continues, they get tired and their music energy starts to weaken. On the other hand, the background noise, dark energy from the audience, the air conditioning, etc., remains constant. Eventually, this constant noise becomes the dominant sound in the auditorium.
So it's like the universe is becoming quieter, but the background noise is staying the same, thus becoming more dominant.
Precisely. And if we project this trend back in time, it's clear that at very late times, dark energy becomes the only significant component of the universe.
Fascinating. But what does this mean for the fate of our universe?
That's a question for the ages. But it's part of what makes exploring the cosmos such an enthralling journey. Interestingly, in the early universe, it wasn't just matter that had a higher density. The density of radiation also increased. Each quantum had a shorter wavelength, a higher frequency, and a greater amount of energy.
This makes me think of when I was a kid, growing up in Pernambuco. I remember having this tiny, cramped room that I shared with my two brothers. And with time, we each accumulated more and more stuff. Toys, books, clothes. The room felt like it was shrinking, but in reality, the amount of stuff was just increasing.
Hey, that's a great analogy. The universe was sort of like your childhood room. As it expanded, its conditions changed. Today, it's mainly dark energy with a significant amount of normal matter and dark matter, but with only a tiny proportion of neutrinos and photon radiation.
But it wasn't always like this, was it?
Right. In the early universe, when it was first forming neutral atoms, it was mostly dark matter with some normal matter. Photons and neutrinos were also important, making up around 10% of the cosmic milieu.
And just like we eventually moved out and got our own rooms, the universe kept expanding, changing its composition along the way.
Indeed, and by observing the redshift distance relation across our cosmic history, we can determine very accurately what must be the contents of our universe smoothly throughout time. The same measurements that reveal the presence of dark energy also tell us about the energy contents of our universe, both now and in our cosmic past. It's interesting how once we know what the universe comprises at any given point in time, we can determine the relative energy densities of every component. To do this, we make our best measurements of what's in the universe and how fast it's expanding today, and then extrapolate backward.
That's kind of like how my mom used to guess how tall we'd be when we grew up based on how fast we were growing as kids.
Hey, that's a good way of putting it. If we extrapolate from our current measurements, we find that our universe today is expanding at around 70 kilometers per second per megaparsec. It's made up of around 68% dark energy, 27% dark matter, 4.9% normal matter, 0.1% neutrinos, and 0.01% photons. Other forms of energy, including cosmic strings, domain walls, and so on, make up a negligible amount.
It's fascinating how much the universe has changed over time. It's like watching a black and white photo slowly fill up with color.
Exactly. And you might be wondering, where did all that energy that was once present in the form of radiation go? There are a few ways to look at it. One is to say that the radiation exerts pressure on the boundary of the observable universe, losing energy as it does work in causing the universe to expand. Another way is to say that the expansion of the universe is adiabatic, meaning it guarantees constant entropy but not energy, temperature, pressure, or volume.
The universe sure is full of mysteries. It's like when we used to play hide and seek as kids, and the whole neighborhood was our playground. Some hiding spots were easy to find, but others took a lot of searching, and sometimes we'd discover completely new places we'd never seen before.
Now you might be wondering about energy conservation in an expanding universe. To have a conserved quantity, something that can be transferred or converted from one form to another, but cannot be created or destroyed, there needs to be an associated symmetry. But the expanding universe breaks time translation invariance, the symmetry that corresponds to conservation of energy. So energy is not conserved in an expanding universe.
Can you give an example to make this clearer?
Sure, think about a marathon race. The runners all start at the same place at the same time, right? But as the race progresses, the runners spread out along the track. The total energy of the runners, their combined kinetic and potential energy, is not the same at every moment during the race. Each runner's energy changes as they run uphill, downhill, speed up, slow down, and so on. In the same way, the energy of the universe isn't the same at every point in time.
So the universe is like a marathon race that's still ongoing?
Exactly. And at the earliest times, there was only radiation. After the Higgs symmetry broke, many particles and antiparticles gained positive, non-zero rest masses and started behaving like matter. However, as the universe cooled, there was less energy per collision between any two quanta to produce new particle-antiparticle pairs. Eventually, these particles and antiparticles annihilated away, leaving only radiation.
Just like runners dropping out of a race over time?
Right. And by the end of this cosmic race, the radiation energy density was billions of times the matter energy density, and around a decillion times the dark energy density. Now let's visualize how the universe expands. Even if we ignore everything else, the stars, nuclear reactions, structures that form, and so forth, the universe continues to expand, and the relative energy densities of different species evolve according to their nature.
Is it like watching dough rise in a bread machine? It starts out small and dense, but as it expands, it becomes larger and less dense?
Absolutely. For every factor that the universe expands, radiation will have its density drop. Think of it like a loaf of raisin bread. As the dough expands, the raisins, representing galaxies, move farther apart. At the same time, the density of the dough, representing radiation, decreases. The matter's density drops because the volume of space is expanding in 3 dimensions. However, for dark energy, its density remains constant.
So the raisins are getting farther apart, the dough is less dense, but the overall weight of the bread remains the same?
That's right. From the time that the universe was 1 second old until today, 13.8 billion years later, the universe has expanded in each dimension by a factor of around 4 billion. This means that the radiation energy density has dropped by a factor of more than 10 to the 38th power, and the matter energy density has dropped by a factor of nearly 10 to the 29th power. But the dark energy density hasn't changed at all. So, unless your dark energy, time, evolution, and cosmic expansion will eventually dilute everything else. For radiation, the worst of it has already occurred. Quite a journey, isn't it?
It's like a cosmic roller coaster ride, indeed.
And there you have it. We've gone on a cosmic journey, starting from the birth of the universe up to the present day. We've learned that the universe is primarily composed of dark energy, dark matter, and normal matter. We've discovered that despite the dramatic annihilation of particle-antiparticle pairs creating a burst of radiation, radiation isn't the main player on the cosmic stage. Instead, it's dark energy, behaving like the very fabric of space itself, that dominates the universe's energy budget.
Absolutely. And not to forget, we've learned about the cosmic marathon, where energy densities of radiation and matter decrease as the universe expands, while dark energy remains constant. So I'd say we are all just running in a cosmic marathon, eh?
Indeed. From the radiant onset to the expansive dance of galaxies, we've seen how the universe changes its energy rhythm, all while keeping the cosmic music alive. And if that isn't a plot twist, I don't know what is.
Right, folks? If you enjoyed our cosmic journey today, don't forget to blast the like button, share your thoughts on this cosmic plot twist in the comment section, and spread the cosmic love by sharing this episode with your friends.
Thanks for being with us on this journey through time and space. Stay curious and keep exploring.
Until next time, folks, goodbye and keep looking up.
I found this fascinating exploration of the universe on the Big Think site in an article titled Ask Ethan, Why Doesn't Radiation Dominate the Universe? By Ethan Siegel, published on January 12, 2024. Check out the full URL in the video description if you're as intrigued as we are and want to dig in further. Now, I'll catch you on the flip side, explorers.